So now we move on to chapter 34, which is your basic mean value analysis. Okay. So we will first do analysis for open queuing, right, an open network. So I have a network of queues, but the network is open. So there is one input point, one exit point. Right. So we saw earlier as to what can be open queue in a transaction processing system where you go through multiple queues, transaction arrives, gets processed and leaves. Right. Even our CPU system can also be looked at that. It is not necessary that it should be a closed queuing network, right? Because simple that with that there is your CPU is there, devices are there, jobs keep coming to the CPU, they get processed, they leave the system, right, without having to do the circulation business. In circulation you are always assuming that there is always a replacement job for a given job that is completing. In open system, job arrives, finishes, leaves, right, just trying to find out the average response time in the system. It depends on lambda. In this case a closed system, it depends on n, right, that is the main system parameter. Okay. Okay. So the arrival are assumed to be Poisson arrivals. With rate lambda. Okay. And the servers are of two types. Okay. So one is an so called finite capacity, this is a finite capacity service center, which means that the service time or the service distribution, right, does not depend upon the number of customers in the queue, it is independent of the number of customers waiting in the queue, which is your MM1 system basically, right. So nothing to be, right, example, right. So this is with here we are going to look at exponential service time, but right. So this is a single server with exponential service time or standard, okay, or the server could also be a simple delay center, right. We talked about MG infinity or MM infinity before, right. So called delay centers. So delay center is nothing but a device that introduces a constant amount of delay, right. So there is no queuing in that particular subsystem that you are entering. Whatever you enter, you always spend SI time units, the service time, then leave that system, right. So there is no queuing in at all. So that is the actual system. From a queuing perspective, we represent that as a MM infinity, right, where for whenever a customer is, there is always a server created to service that customer, and then you get serviced. So there is no real upper limit. Sort of like your web browser, right, or web server. Anytime there is a HTTP request, you spawn a new thread and service the new request, right. In theory it is not infinite, but practically you make, in theory it is infinite, but practically you might have, right, some limits on, like no more than 1,000,000 threads or something like that. So essentially the time spent in the system is simply, right, so the time delay, the time spent service time, and you can derive this very simply, right. If you look at an MMM system, we have after some point the service time is simply m mu, right, after m it is mu, but in this case it will be n, if the system state it will be simply n mu, right. So you can very easily derive that the service time, we can go, maybe that is for a final exam, you can figure it out, right, MMM infinity. The results are there in the book, the derivation is fairly straightforward. Okay. So these are the two service centers. We are not looking at the so called MMM systems, right. These are load dependent service centers, right, where depending on the number of customers in the queue, the service center's capacity will be increasing. If there is only one customer, the service capacity is mu. There are two customers, service capacity is 2 mu, 3 mu and so on, therefore that is variable, that is called load dependent service center, right. So that is for chapter 36. That comes later, we are looking at a simpler system now. Okay. So this is my specification. So I have a network of queues, standard Poisson arrival, but these are very right. This load dependent service center is not being considered here. Okay. Okay. So now, based on what we saw in chapter 33, we are just going to have, if I give you a queue of networks which is open, you should be able to simply run through that like a machine and say this is a delay, this is the average delay, this is the average queue length, average utilization, average throughput, all that is very simply computable. You can write a 10-line program to actually do that, and that is basically what you are going to list here. Okay. So the only addition that you will see here is for all fixed capacity service centers, we will call this FC from now on. This the response time is simply that. What does that mean? You know this, we have seen this several times before, right? So the time spent, the response, the total time spent in a Qi is simply this average service time, which is Si into 1 plus Qi. So when I arrive to the queue, I find Qi customers waiting, right? This is E of Nq at the time of arrival. So I have to wait until all these guys finish their service. This of course requires a memoryless property assumption that we are sort of, this is not an operational law, this is a convenience law, right? So therefore if there are Qi customers, they will all take Qi into Si, even though this guy might have partially finished service, right? Simply saying when I arrive there are Qi guys, the remaining service time is simply Qi, right? We did this residual service time analysis separately before, but in this case we are assuming that all Qi customers will take on average Si time units. So I have my total waiting time, total response time in this device is Si, which is my own service time, plus Qi into Si for all the other guys, that is all. This is only addition from what we saw in the previous chapter. Okay, this is one extra rule. Okay, so this is not an operational law. Okay, so now I list a series of steps, right, to sort of figure out all the performance metrics for this given open queuing network. We look at an example, but the steps are as follows, right. So the first thing is I will be given lambda for sure, right, these are my inputs, I will be given SIs, I will be given VIs in some form or the other, right, without these I cannot proceed further. So therefore the system throughput, assuming flow balance, right, simply lambda. So this implies that the number of jobs leaving on average equals to the number of jobs arriving. So my first, remember everything depends on this x, so we got x, then we can get our xi's because we know Vi, right. So Vi has to be given, otherwise we have to look for it in the description. If it is not there, then it is tough luck. So Vi is either measured or something or the way, some way or the other, looking at logs we can find out what the average Vi is and so on. Then we know that Ui is basically okay. So then after we need to find out this Qis. Okay. So Qi is equal to Xi Ri, Little's law, right, and Xi and Ri we express that in terms of our assumption here that Ri equals Si into 1 plus Qi. Which by the way happens to be Ui. So therefore Qi equals Ui by 1 minus Ui, and this by the way we have seen already, right, this is the re of n, for a single queue, row by 1 minus row, right, just derive same thing is showing up again. So we know the expected number of customers in any queue is simply, once we know the utilization of the queue, it is simply row by 1 minus row, so same thing. So basically, right, so I am getting my x, my u, from a u I can get the q, from once I get the q then I can get my r, right. So ri, I can get ri whichever I want to, once I can use this expression, right, it is basically q by x, or I can also derive that to be and by the way this is right, or 1 minus 1 over mu minus rho, same thing is showing up. This notation is different unfortunately, but that is all, right. So basically I can look at every queue, figure out all these values. So once I get all of this, and for delay centers Ri equals Si, there is no queuing at all, right. And the number of customers queued in an infinity queue is simply rho. If you go back and look at it, it will be just rho. So again we can derive this if you want, this is Ri into Xi, right, the same formula as before, but Ri we said is Si into Xi, which is, I will go to the next page, you got this for R equals S, right. So S into X is basically, X is again X into Vi, right. So if I can go to the next page, can I? That equals yeah, Si into X into Vi, so that is basically X Vi Si, Vi Si is nothing but Di and X Di is nothing but Ui. So Q, number of customers queued is simply equal to the utilization of the device, and infinity Ui need not be less than 1, right, because there is that restriction is not there. You can have as many customers as you want, you will always have a server waiting to serve you. So therefore this Ui, in other words Qi equals Ui, need not be less than 1. I can have 100 customers sitting in the queue, right. That restriction of row less than 1 applies only for the MM1 infinity, not MM infinity. So once I get all of this, then I can compute my R, right. R is simply RIVI. So that is what I basically want to find out, right. I know the throughput, I know the response time. So this you can very well, right, implement as your next assignment. Open queuing network, you know how to connect, you know how to do a single queue, connect the queues, feed in traffic, you can then verify whether all of this is correct, right, or whether this mean value analysis is correct or not. So that could have been your project 3, but it is not. I figured that closed queuing is more interesting than open, so if you want you can do open queuing the same thing, right, just slight modifications, but you are going to do open queuing network. Those who have finished project 2, that will be your assignment, that is almost ready, tonight it should be uploaded. Okay, look. So let us look at an example. We have been going for almost 50 minutes with only Xi's and Ui's. get that. So that is my classic network, right? Two disks, one CPU. And occasionally CPU finishes the job and the process leaves the system. Okay. So now for the input specification. So somebody as system administrators given you the logs and you have done some measurements, right. So the observation period T is 3600 seconds. So you have taken 1 hour's worth of data. So then the number of client requests or job requests, right, that you read from the log file is 10,800, and then every time, right, the log will tell you CPU is getting used, CPU is starting use, somebody is written, right, start of CPU utilization, end of CPU utilization. So you are measuring the CPU utilization time, right. So the busy time for the CPU was 1728 seconds, then your disk A busy time for 1515 seconds, and the disk B then the system also, right, from the log files you found that the number of completions or visits, right, to disk A, total number of visits by all the jobs was 75,600, number of visits to DB was 86,400. This is what we are given. Anything else we need? No. Okay. So with this, so you are given a network, you are given some of these operational values measured. Now the goal is to find out, right, what is X, what is the D, and the goal is not just to find out the response time, the goal is to use this to find out where the bottleneck is and then try to enhance your system performance by removing bottlenecks or making some disks faster and things like that, right, that is the whole purpose. If it is today 36, there are 10,000 jobs per unit time, what happens if it is 20,000 jobs or 60,000 jobs arriving, then how do you use these values to extrapolate and then find out what will be the future delay, right. So that is the whole idea of this performance evaluation. Okay, so how do we start? Where do we start? Start with X. Before X we need lambda. Okay, so what is lambda? This is the number of jobs per unit time. What is that? Okay, so therefore so X equals 3, done. So what is next? What can I figure out? Xi. For Xi I need Vi. What is Vi? So we know the right. So Va, the number of visits. How many visits were made by the jobs? There are total 75,600 requests to disk A, and there were 10,800 jobs that finished. Right. So this is assuming that we started with no job at time 0 and no job at time 3600. Right. It's possible that some jobs still lurking. We are just ignoring all that. We are assuming flow balance, that whatever started is gone. Right. Otherwise, this could be some other job that started even earlier that is still requesting. Right. That's still going on in the system. So there are some sort of convenient assumptions we are making by ignoring all those older jobs. Okay. So we find that there are 75,600 requests totally made only by these 10,800 jobs that completed. Therefore, each job must have requested on average 7, right? And this is also average. We do not know if every job requested 7. We are just saying that average is 7. And next one is VB. So this is again conveniently given. No need for a calculator. It's 8. Right. We said VB had disk B had 86,000 requests, 400 requests. So VB equals 8. And we know that every time you go to a disk you have to go to the CPU, right? We saw this before. So vCPU is simply 1 plus and one final execution where there is no disk access required. It is simply computing that the process finishes, that is the outline, right? So vCPU so now we can do all the Xis. So now we can look at the throughput of every device. So throughput of each device then will lead us to other things, right? So XCPU is so the CPU handled 48 requests per second, right? And this disk handled okay. Too fast. Should always do this. Now what do we need? Service times. So what is the service time? Average service time spent at the CPU, disk and so on. Available? So what is the average service time for the CPU? You have the busy times, right? Some of the busy times we can figure out. So there, you know that the total busy time was 1728, right? Divided by the number of jobs that completed, right? So we can actually compute the dCPU first. If I know my dCPU then, right? So dCPU is what is actually given, the total demand on the CPU. So dCPU, total time the CPU is busy is basically the demand, right, made on the CPU, and so that is totally it was busy for 1728 units of time seconds, and the total jobs that finished were 10,800, right. So each job on average the total demand made by that job is So dA is 0.14 and then dB is 0.24. Now it's better that you verify these values because the book is got a huge error list of errata. So I found my demands for each of the devices. So once I know the demands, how do I get the service times? D equals VISI, right? DI equals VI into SI. Total demand is the number of visits, average visits per job into the average service time. So SI equals DI by VI. So therefore SCPU so the service time for that is 0.02 seconds, service time for A is also 0.2 seconds and service time for B is 0.03 seconds. Sorry, it is not the book's fault, it is my eyesight's fault. I wrote my 2 as 1. So which is the bottleneck device? Disk B, that is taking maximum service time, right? Maximum demand is B. So if I want to reduce that service, either service time is what I can do, right? So or I can even reduce the number of visits. So how will I do that? I can either put a faster disk or number of visits, how do I reduce between the two disks? You have to basically move some file system, right, some part of the file system to disk A because it is faster, that way you reduce the number of visits to disk B, right, because some files are sitting there that you are accessing a lot, but unfortunately the disk is slow, so you should try to basically balance your file system such that you essentially come up with almost equal, right, DI. Okay, so now we have found S also. So now once I find S, then I can find I do not really need the QIs, right, because once I get the service time, well, I need the utilizations. Yeah, sorry, we need UIs before that. What did I do? Okay, so then we will find out the UI, and UI is given by XDI, right. So since I know D, I know X, so therefore U CPU, the utilization of the CPU is 3 into 0.2. 0.18, utilization of A is 3 into 0.14, that is 0.42, and UB is 3 into 0.72. Again check, right, when you come to this stage in your exam, you find that UI is greater than 1, you know that somewhere you went wrong, all U should be less than 1, and also the highest utilization is for disk B, that is a bottleneck, right. So just take a moment to check those. Alright, so now I can use my standard formula. So this is S by 1 minus U CPU, right. This is again 1 minus 1 by rho, 1 by mu into 1 over 1 minus rho, our standard MM1 formula, just showing up differently, right. Service time by the time that the server is actually idle. So that is now 0.01, 1 minus 0.48, so this is 0.0192 seconds. RA likewise 0.0345 and RB is 0.107. Again check that disk B has got the highest response time, so that is your slowpoke. and then I can compute my overall system response time per job is using all these values derived so far. So what is R? What's the average response time? We have now everything at hand, the last formula. Okay. So now with this log file you have been actually able to translate this into this set of numbers. Now if your boss says, right, so what if boss is not happy with 1.4 seconds, that is too much response time, we want to reduce the response time. So the boss says do something about it. So you say, I'll just say one, right, use, yeah, so these are the options, right. So use a cache for disk B to reduce the service time. Okay, but if I am going to cache, that means I am going to have more CPU intervention. So therefore, while the CPU utilization, this is again a guess on your part, right, while CPU utilization goes up by 30%. Basically your CPU response time, right, the service time will be higher for the CPU because, so you are trying to, right, look at some sort of compromise. So now you do not have to go and actually build a system, right, that is going to have that kind of 10%, simply plug these numbers, you can now come up with an approximate idea of what the performance should be, then you can make an intelligent choice as to whether to, this is worthwhile or not. So that is where your analysis techniques come in handy. Okay, so that is your example analysis for a complete queuing system. So given any open queuing network with only one entry point, you can simply do that. What if the open queuing network has multiple entry points, as in a packet, right, there are several routers, there are some packets getting injected here, then also along the way you can get new packets added at every part of the system, that is also an open queuing network, right, and multiple exit points. Well, we will not worry about that now, we will leave that for some other class. Okay. So this is a single input single output system. So questions on this so far? None? Alright. So that was the open network. Now let us go to queuing network, closed networks, right. So for this the technique used is what we call as mean value analysis, right. So closed queuing networks. So in the closed queuing networks your input is no longer lambda, it is an n, right, and everything else is similar to the other system. So use mean value analysis. So this will be applicable only for the systems that meet the conditions for product form solution. Initially it was just the MM systems, but then later on a lot more systems have been listed. I just mentioned those to you, book lists them, right, from this BCMP, Chandy and others paper 75 that showed a lot of conditions. So there are more general networks that can be looked into. We are just making this assumption, right, only for the so here again we are only looking at the two systems where there is fixed service or fixed capacity and delay center. So I am not considering MMM systems, just MM1 systems and delay centers, MM infinity systems. Okay. So now let us look at what is involved in actually trying to find this out. Analysis is more or less similar to what we saw before, it is an iterative process. So the system is, right, you have a defined system, you start with just one job, it enters system, it goes device by device, it finishes, then you replace the next job and this first job is complete. Then you inject, you say okay that this is the, we saw what R of 1 is, right, it will be D and so on. So then you inject one more job and see what happens to the queuing status, right, and you keep on increasing value of n until you find out some sort of optimal value for n. Okay. So to do this analysis, so you will be given n and you want to find out the response time with n users and the throughput with n users. R of n, x of n is what you are looking for, n is input, Si, Vi, all those things are given to you. Okay, alright. So the basic premise that it uses is, right, this was actually shown, right, this is not a guess, so it was shown that, and we are not really worrying about it, but this Q is an important, right? The number of elements queued in a device is what you want to know. Once I get the Qi, then I can derive many other things around it. In the last open network, it was Qi equals Si into 1 plus Qi, right, that is known, but in this case I have a similar formula, right. So the number of customers queued in device I when there are n customers circulating in the system, okay, is equal to Si 1 plus Qi, then something else, what would that be? So when the nth job arrives, right, the delay it faces is the service time for itself plus the number of customers queued ahead of it when there were n minus 1 jobs in the system. That's the basic result that we use. We are not proving it, we are just taking that as matter of fact. Okay. So the previous expression was Si Ri equals Si into 1 plus Qi, here it is simply Si into 1 plus Qi n minus 1. So to compute values for R of n, x of n, I need to know the corresponding values for n minus 1. Essentially it becomes a recursive process, right. So from 1, 2, 3, 4 and so on. I am sorry, n is the number of jobs in the entire system, the number of jobs which is distributed across these several different queues. Okay. So yeah, so let me put what this n is the total, yeah, when there are n customers the length of Qi, length of yeah, ith device Q. That the notation, that's the notation that we are using. Okay, I will write that down. I will put that in the next slide. So Qi of n is the number of, or is the average queue length at device, that is i's queue when there are n jobs in the system. So if my degree of multiprogramming is n, then this is the number of customers I will see or jobs queued up at the ith device. If I know the number of jobs queued at device I when there are n minus 1 jobs in circulation, using that I can find out the number of jobs when there are n jobs in the system. That is the formula that you are going to use, and it is exactly similar to the other one, right. When there are n minus 1 guys, there were so many jobs queued, then when the nth guy comes, right, this again we can pretend this is true, right, we can just sort of logically derive that, yeah, this should be okay, like we did in the other case, but to actually prove that, that is done in some 1980 paper which we won't have the time to go through now. Okay. So now the steps for MVA. Okay. So the basic steps, right. So initialize n equals 1. So one customer we can always find out, do you know what the R is, we know what the D, right, R is going to be simply D, right. So compute R of n. So we assume that we are given Si and Vi, that is pretty much all that we need, right. Service time plus the number of visits to each center, that is about it. And then from there, right, we know what R is. Ri in this case is simply equal to the service time because there is no queue in the system at all, right. Your Qi of 0 equals 0, right. So when I start with that, so I can simply compute that when there is no queuing, everybody is only job floating around. So Qi of I equal of 0 equals 0, therefore I can easily compute R of n, right. This is from my Rivi, and initially for n equals 1, Ri equals Si. So then when I compute this, now this is a time sharing system, right. So we will have this think time also introduced. So I can start with computing R, compute the throughput because I know the response time. Then I can compute the each device's and once I compute X, I can compute Q. So Qi of, so what is Q equal to? XR, right. So this is simply Xi with n, Ri with n. So that completes one step of the iteration. Start with 1, n equals 1, compute R, then the rest of it naturally follows. Now I have basically computed my Qi of n. So now I go back and then I will, to compute R of I, right, I will be using my approximation here, right, and that is your mean value analysis algorithm. So given a value of n, you simply have to run this n times to find out. And if it is a delay center, Ri is always Si. Note, for all delay centers, Qa of n equals 0 and Ri regardless of the number of customers is Si. That is your end of MVA. The book actually gives you an algorithmic description, but that is basically the same thing. If you want to implement, you will simply use that description. So now let us look at that same example, right. So this is now that CPU, then it goes to one of two disks, okay, and then when now and then the job finishes, this is interactive system. So there is a delay center, right, which has infinite, this is a delay center, let us put that as DC, they are infinite. So delay center is where your interactive terminal is sitting and thinking, and then after thinking it comes back and joins your queue. So this is technically your inline and this is technically your outline. So whenever a job is coming in from here to here, that means that that job is basically completed, right, and then it is a new job that is replacing it. So we measure the jobs traversing this link, the out link, out to in link, that is where we would say that is where throughput is measured. Okay, this is what we have seen before. So now in this system we have to find out, right, what is the throughput of the system as n increases. Okay. So the input right that is given to us, that VA is 10 and VB is 5, okay, and the service time of the first device is 0.3 seconds. This is different from the just previous example that we saw, right, so do not get confused. So I am given S and V, then well, just for change they are also giving us D, right, for the CPU, and that Z is 4, N equals 20. So with this scenario, what is the average number of jobs completing and how long does each job take to finish in the system? Okay. So we need to find out what. So where do we start? I know DCPU, I should find out SCPU, right, service time for the CPU, because that is what I am using in my calculation. So SCPU equals DCPU by VCPU, which is 2 divided by 1 plus 10 plus 5, so that is 1 by 8, so it is 0.125. Okay, so we have pretty much everything to get started. One questions? Okay, so initialization. So this is our execution of MVA. We just said Qi of Qi equals 0 for all I, right. Then this is n equals 1. So we simply have to find out all the R's, right, Ri's, get the R, get the X. Okay, so I am going to wait and watch when you tell me the values. So what is going to be X? No queuing, right, therefore Ri equals Si. So response time is five, 6, 3 plus 2 plus 3 plus 1 plus 2. So and then X is 6 by n equals 1, R is this, Z is 4.1. So if I only have only one job in the system, my average throughput is 0.1 because each job takes 10 seconds, right? So throughput is just 0.1. Then we wanted to compute the queues, right? So q CPU is now equal to, so q equals xr, x I know, r I know. Q equals xr, yeah, right. XARA, sorry, XARA. Yeah. And we always know that this is true, right. So that is 0.1 into 16 into 0.125. So this, so the new value for q CPU, which was 0, is now equal to 0.2, and the value for this one is equal to so that is my end of first iteration. I have new values for q. And again, as a check, you should note that the queue length should always be less than or equal to, what should the queue length always be bounded by, 1 or queue length, by n, right, because you cannot have more than n customers in any queue, total system capacity is only that much. So but how come the sum of these queues is not equal to 1? I have only one customer circulating, 0.2 plus 0.3 plus 0.1, so what happened to the other 0.4? Delay center, right, thinking time. So that is what that is capturing. Alright, so now we can sort of mechanically run through these things, right. You can write a small program, you can simply just compute all of this left and right. So if you want, I can put in step by step, otherwise let you go compute the step by step and I just give you the numbers as we go along, right, because it's more interesting. In the first step, yeah. So this is that customer is in the delay center. Well, before you start, yeah, the guy is all the queues are empty when you start the system. These 3 queues are what we are looking at, right. In the relay center there is no queue as such, right. If a customer arrives, always there is service time. So there is, except that when you finally finish and go to the delay center, you will spend a constant amount of time before coming back to the system as such. Okay, so R, I am going to just write. So the new delay is 7.4, because again if you will, well, just write at least 1. So the R CPU is now S CPU into 1 plus the most recently computed Q CPU, which is essentially 0.125 1 plus 0.2, right, that is what we computed, that is equal to 0.15 and so on. So if compute this way, right, RA RB, RA is point and so on, so all of these basically feed into your R. So now the response time, if we add one more job, is increased to 7.4 seconds, slightly higher than D, but still bearable, one would say, okay. So then X equals 2 by 7.4 plus 4. So now my throughput started increasing. I am able to handle, I am not getting 2 jobs per second, but it is better than what I had before, right. And then you can now compute the new Q CPU values. So now your Q size starts increasing, so this is 0.421, QA is like we did last time, right, x into Vi into the last computed Ri. So remember that the Ris keep getting updated in every step, and the QAs also keep getting updated in every step. So you will always use the most recent value for the Q and R. Vi does not change, but R changes, Q changes, and that is what is repeatedly used in this. Okay, so dot dot dot, if it is a program, just run this forever, and we said n equals 20, right. So for n equals 20, what should be the throughput finally? So what could be the throughput? N is fairly large now, well, not very large, but what will be the upper limit for throughput? We will be hitting the 1 over Dmax limit, right, and what is Dmax? Dmax is, what is the value of Dmax? dA was 3, dB was 1, and dCPU was 2, so Dmax is 1, right. So it should be 1 by 3, cannot finish any better than 1 jobs every 3 seconds. So from 0.1 I went up to 0.33, that is about the best I can do with this system. Okay, and then R of 20 equals, again, so this is actually computed by your, you will find this ends up with 0.33 if you run it long enough, and R of 20 is again computed by our algorithm, which is coming out to 56 seconds. Okay. So the response time has gone up from 6 seconds to 56 seconds. So that is fairly, depends on whether you want to operate at that level or not, but that is what it is. I am sorry, the 3 demand values are 1, 2 and 3. We never computed demand value for A. Vi into SA is 0.3 and Vi, oh 0.3, oh my 5 looks like, S looks like 5. So yeah, so 3. So R of 20 is 56 seconds. Now what is the corresponding, remember that for response time I can get the lower bound, right. So from our bound calculations, what is the lower bound, right? This was again max D right, clearly D is 6, so therefore there is no issue. So this will be max, so that will not show up. N is 20, D max was 3, and always think something, write something, okay, Z minus 4, right. So lower bound is 56, I got it, and our actual computed value is 56. So it is reasonable bound, right. So if you do not want to really go and figure this entire calculation, you can just look at these bounds and say, look, you cannot do any better than 1 by 3 throughput wise, and you cannot do any better than 56 seconds, you cannot go lower than that. So these are just checks when you do this in your exam. That is after running this on the computer. So I am just giving you the values, right. So if you write the source, yeah, you have to write a short program, right. This is a simple program, right. So time of computation for this is order n, right, because each step you are not doing, you are just doing linear calculations, there is nothing. So order n is the computation time, which is not bad by most standards, but people found that when n is very large, let us say I want to do a million, right, customer system, you are looking at web server transactions, million or 10 million customers per second, you can't be sitting there running for 10 million customers to get the result, right. So MVI is good, but the n complexity can be a deterrent if your n is very large, because that is what we always want to try to, not like 10 jobs per second, we are looking at a million transaction coming to a Citibank server, you want to see what is the response time, right. So to get around this order n business, there have been lots of approximations. So there is one particular approximation that this book discusses, which I am going to present now. I am not sure if this is still the best approximation. This was 20 years ago that the book said this is a good approximation from like 1976, around that time, right. 70s 80s time frame, they said this is an approximate MVA, and that reduces your search time or the computation time from order n to some small order k. It is an iterative algorithm, it will converge, it might not converge, but it gives you usually results in less than n time units. So if I give you a very large n, you can simply iterate, right, with this approximation and get similar values as to what you would get with your regular MVA. So we will come and look at approximate MVA on Friday, right, as to what the changes.